When long-span structure is unavoidable, by bending the member, we can drastically improve its strength. When the long-span structure is straight, the bending moment at the middle is huge. By introducing a bend member, which better known as arc, the forces exerted on structure are now inducing compression in member rather than bending. This is beneficial to the structure, especially if the arc is made of reinforced concrete, where the compressive resistance is superior to its bending resistance. Let's look at our arc problem. This is a three-hinge arc. The elevation of support A is higher than support C. The crown of arc, point B, is 2 meters higher than point A. Cable parallel to arc springing line is provided to connect point A and D. Two concentrated loads with the magnitude of 15 and 10 kN are exerted on this arc. You may find this problem in the 7th edition Structural Analysis book authored by RC Hibbeler. The objective of our analysis is to determine the support reactions and force in the cable. To do so, we need 4 equilibrium equations to solve our 4 unknown forces, 2 from support A, 1 from support C, and 1 from the cable. We construct our first equilibrium equation by taking moment about point A. This equation does not involve cable force T, and therefore, we will be determining the support reaction Cy. From calculation, the value of Cy is 9.55 kN. By taking equilibrium in y direction, the value of Ay is calculated and it is found to be 15.45 kN. Next, we cut the arc into 2 parts from point B. Focusing on the right part, we form equilibrium equation by taking moment about point B. The unknown force T is included in the equation. Through calculation, the value of T is 4.33 kN tension. By taking equilibrium in x direction, the horizontal force at point B, namely Bx, is 4.33 kN acting in the direction opposite to T. On the other hand, By equals to 0.45 kN. By transmitting the Bx to the left part, we are now having enough lateral forces to solve for Ax. By taking equilibrium along x direction, the value of Ax is 0. Alternatively, we can construct equilibrium equation by referring to the whole structure. Ax will be 0 since there is no other horizontal forces exerted on the arc. At this point, we have achieved our objective by solving the support reactions and cable tension. Now let's extend our scope to determine the internal forces. First of all, we need a function describing the geometry of arc. Assuming this is a parabolic arc, its curve function involves the height and base length of parabola. Let us draw a horizontal line at point A. The arc is now a parabola intersecting the horizontal axis at 0 and 5 meter marks. Therefore, the base length of the parabola is 5 meter. The height of parabola is 2 meter, measured from horizontal axis to the crown. By substituting the values to the general equation, we obtain the parabolic function for our arc. We are safe to exclude the part of parabola below the horizontal line during determination of parabolic function. This is because the part does not provide us any essential info, and yet it is predictable by using the function we derive. Then, we will be determining the first derivative of the function. By doing so, we have a function that tells us the gradient of tangent at any point on this parabola. From the gradient, we can determine the inclination angle of internal forces at that point. The sign convention of internal forces is the same as what we use for beam and frame. The segmentization of arc is done by splitting it virtually at the points where loads are exerted plus 1 at the location of internal hinge. As a result, we have 5 segments for our arc. Let's check out the first segment. The limit of this segment is from 0 to 0.5 meter, measured horizontally from point A. The external forces included are reaction AY and cable force T. By using equilibrium equations in global X and Y axis and bending moment about the cutting point, we can build 3 equilibrium equations correspond to 3 unknown internal forces. However, we need more than that to form general equations for the forces. 2 of our equations now consist of unknown axial and shear forces. For the ease of future application, let's simplify the simultaneous equations. The axial force is first expressed as a function of shear force and inclination angle. The expression of shear force is then constructed by substituting this correlation into equilibrium equation we made for x-axis. The same technique is applied to other segments. An important thing to note is that we need to be careful about the limit and reference point of these segments. The limit of segment 2 is from 0.5 to 2.5 meter. Its reference point is point A, which is the same as segment 1. For 3 subsequent segments, our reference point changes to point B. The limit of segment 5 is from 0 to 0.5 meter, and that of segment 4 is from 0.5 to 1 meter. Knowing the parabola is symmetry over the vertical axis passing through point B. The limit of segment 3 is from 1 to 3 meter. With the internal force functions, we can determine the forces developed for every 0.5 meter interval. Focusing on point B, and check what are the forces developed in point B. We know the axial force is 4.33 kN compression and shear force is 0.45 kN. There is no bending moment at this point. By using the right functions, we can determine the axial force, shear force, and bending moment for the remaining points of interest. At this point, we have successfully produced the internal force diagrams for an arc. The axial force diagram shows the arc is always in compression, which is consistent with the primary intention of using an arc structure. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.